Here is a simple office tower, steel-braced core, 25 stories high. Well, I should say, here will be a simple office tower. It hasn't been created yet. A company has contracted our services as a structural engineering firm to design this building. To do so will require us to apply a variety of mathematical concepts. So, let's get started. Trigonometry, vectors, algebra, differentiation, integration. These are the 5 mathematical concepts we will use to help us get this project started. The project is, of course, simplified, and we're just going to provide an outline today. We're not going to throw you right into the deep end just yet. First things first, we need to survey the site. We need to ensure that the building fits within the proposed site. However, there's a tree getting in the way of measuring the position of the south wall. The blue line represents the south wall. Let's call it AB. Utilizing Pythagoras' theorem, we can measure AX, BX, and the offset XY to find the distance of AB. Now that we've got the base of the site, let's think about the steel-braced core of our building. We need to consider the forces acting upon the building to know exactly how to design it. 2 of the major considerations for any tall building are the wind forces, being a lateral force, and the vertical loads, comprising of the self-weight of the building's materials, and any additional loads from people, chairs, and tables, to name a few. To understand the impact of these forces, we visually depict them using force vectors. These vectors represent the force's magnitude and direction. Let's take a quick look at the right-hand column being compressed. To ensure that this column is structurally sound, we can utilize an axial force equation. One way to apply this equation would be to rearrange it for the purpose of calculating the minimum cross-sectional area required. Once we've calculated this figure, we now know that any column type with a cross-sectional area less than this is not suitable. Now let's have a look at a horizontal beam. This type of beam is known as cantilever. Since all materials are flexible to a certain extent, we do not want this beam to be acting like a diving board. That is, when a force is applied towards the free end, we don't want it to deflect too much. To calculate the deflection at any given point, that is, to verify whether it is within acceptable limits, we use the concept of integration. As just demonstrated, we've seen that beams can bend. Now, we need to know where the minimum and maximum points of bending occur. For example, here we have a simply supported beam. Thankfully, an equation for the bending moment of this type of beam already exists. Applying algebraic concepts will give us the location of the minimum bending moment, and differentiating the equation will yield the location of the maximum bending moment. By knowing these figures, we can optimize the design of the structure. Now that a simple, brief approach has been outlined, it's time for the design to begin, but that's a story for another day. We're all finished, and here is our completed building, all nice and structurally sound. Oh, hang on. There's just one more thing we should look at. We've got this building now, but the client wants to put a sculpture in the foyer. You know, something nice to look at. However, we need to consider the weight to ensure it won't, say, crack the floor. The thing about this sculpture is that it's an abstract shape. Therefore, to calculate its volume, we must apply the solids of revolution concept. Solids of revolution is an element of integration. Basically, it takes a 2D curve and creates a 3-dimensional object, in this case by rotating it about the x-axis. Alright, we're all done here. Mathematical concepts are important and powerful tools with which we can solve many engineering problems. The essence of mathematics is not to make simple things complicated, but to make complicated things simple.